हेलो दिस इज कंक्रीट पाथ। तो आज के लेक्चर में हम स्टार्ट करेंगे बेंडिंग स्ट्रेसेस इन बीम्स। सो दिस टॉपिक इज बेंडिंग स्ट्रेसेस इन बीम्स, बेंडिंग स्ट्रेसेस in beams. So let's say this is your beam. Let's take this as a beam. Now you applied a bending moment. Let's say this is your bending moment. So उसकी वजह से क्या होगा? Your fibers of the beam would get bend like this. So because of bending moment, the fibers bend, let's say in this fashion. Because of sagging bending moment, because of the positive bending moment, you have a sagging curvature. So let's say this one. So if you see, if you analyze that, your top members get compressed, and bottom fibers got that stretched. So bottom fibers got stretched. If you make more detailed diagram, you can show in this fashion. So let's say this one. So your top fibers got compressed, and bottom fibers got elongated or stretched. So stretched. So that means it has developed strains because of compression or elongation. There is development of strains. Those strains develop okay, and so on the top fibers we have compression, and bottom fibers have tension. So there will be some locus of points where there won't be any change in length. So let's say this is length L. Initially the length was L, but then we say that there would be some points on the beam itself where if you join the locus of those points, if you have the locus of those points, we would have strain equals to 0 along those lines. So let's say this is the locus of those points where the strain is 0, and the length here is also L. So we'd say that the locus, we can write that locus of points where strain is 0. If the strain is 0, that means from the Hooke's law, if the bending stress is 0, if the bending stress is 0 on those points in the beam, we'd say we can say that's a neutral surface that we call as neutral surface. So neutral surface we have, that means at the locus of points and that forms a plane. Let's say the plane formed looks like this one. Let's say this is the plane that forms. If we talk about isotropic and homogeneous material, then if you talk about homogeneous and isotropic and prismatic material, then we have the neutral axis forms at the centroid. That we will be showing also through the equation that we derive. So till now you can remember that at the centroidal plane would be the neutral surface. Centroidal plane would be the neutral surface. So where we can say that bending stress is 0 on that plane. So we can say आपके top fibers में compression आ रहा है because compressive strain has developed, members have developed length L minus delta 1, and bottom fibers L plus delta 2. So bottom fibers have elongated. So because of tensile strain, we have tensile stresses developed. Tensile stresses because of bending. So we can call it as bending tensile stresses. So bending tensile stresses, and we can call on the top bending compressive stresses. So this is bending compressive stresses. So now we have few terms that we can discuss. So this is the direction of moment. Let's say this is the direction of moment. You're applying moment in the z direction. This is z direction. This is x direction, and this is y direction. Let's say this is y direction. So you are applying moment in the direction of z. So moment in the direction of z. So we can call it mz. So moment in the direction of z, and the plane on which it acts, moment. So we can write that direction of moment is z. And it acts in plane perpendicular to it. So it acts on the plane that's perpendicular to it. the perpendicular plane would be look like that. This is the plane. Let's say this is the plane on which this acts. So on this plane, your bending moment is acting. So this is the plane that we can call it as plane of couple. So this is an imaginary plane that's called as plane of couple, perpendicular to moment z direction. So plane of couple, or we can say this is plane of loading, plane of couple, or plane of loading. So this is the plane on which the bending moment is finally acting. So direction of moment is z, but it acts perpendicular to on a plane perpendicular to it, that we call as plane of couple. So the final conclusion is that moment z direction perpendicular to plane of couple or plane of loading. So one conclusion. So next one is that we have concept that we call as that bending occurs in plane of bending. Bending occurs in plane of bending. Plane of bending. So we have some plane of bending, POB. If the bending occurs in the plane of bending, that means what this statement means. So we say if the moment z direction, so direction of moment was in the z direction, moment z was in the direction of z. So moment z direction, if it is parallel to neutral axis, or we can say neutral surface, neutral axis. So neutral axis. So what's neutral axis actually? So once we have neutral surface, when you have neutral surface developed, so this was your neutral surface. Neutral surface. When we cut any section, let's take any section. So if we cut any section, let's take some particular section. So if we take a section, this is our section. So we would say we'll take that section. So this is our section. Let's say this direction is z direction and this is y direction. So there is some that points on the section where the bending stress is 0. That axis developed, imaginary axis developed, is the neutral axis where the bending stress is 0. So this is an imaginary axis in the section where the bending stress is 0. So the concept was that if the moment z direction, that is z direction, if it is parallel to neutral axis direction, then we say that bending occurs in plane of bending. So if we have, from this case, we said that this was your neutral axis direction, and z direction was also same. So we say neutral axis parallel to z direction, then we can say bending will occur in plane of bending. So this is our one more point, that plane of bending is perpendicular to neutral axis. So we had two conclusions to draw. That one is your that moment z direction zz, that's perpendicular to plane of bending or plane of couple, plane of loading or plane of couple. Next one is that plane of bending, or we can say neutral axis is perpendicular to plane of bending. Now from these two, we have one concept of that's called as symmetric bending. Let's take a rectangular section. So initially the beam looks like this one. So you applied some moment m in the z direction. So moment z direction. Now what would happen? That we can say, so this is our section somewhere here. So you cut a section here. So this is z direction. So this is, let's say this is z direction, and moment you have applied in this way. This is moment z. Now we can say, from the conclusions we have that moment z direction perpendicular to this direction, you have a plane of couple or plane of loading. So if you draw perpendicular to the z direction, let's say this is perpendicular to this, then we can call it as plane of couple. So plane of couple is perpendicular to this. Then we have one more thing, that's neutral axis. So we know that neutral axis is same here also. Neutral axis is parallel to here. Neutral axis is parallel to z direction or moment z direction. Then we can say draw one more perpendicular perpendicular to neutral axis, that we call as plane of bending. So if plane of couple is coinciding with plane of bending, then we say this is symmetric bending. Symmetric bending. So if we have one more definition, that simplified definition for this symmetric bending. Let's say you are having this section. Now you can have, let's say you can have a symmetry. This we can have a symmetry here. We can call it as that axis of symmetry. We have an axis of symmetry here. Symmetry. We can have an axis of symmetry. So one axis of symmetry would be this one, and next one would be this one. So we have two axes of symmetry. And let's say you have axis of symmetry. But one thing is that if you talk about one concept that is called as principal axis. So as we know that moment of inertia or second moment of area, it's a tensor quantity. So it is a function of, it's a function of plane. So similar to that of stresses. You have a moment of inertia that is a function of that plane also. So it's a tensor quantity. You can perform transformation of those inertia, or you can use Mohr circle also, similar to that of stresses, to get the location of principal planes. We know that principal plane. What is the principal plane in the stresses? We say that principal plane is the plane where your shear stresses is 0, tau xy is 0. And we have two principal planes at angle of 90 degree. We know that we have two principal planes at an angle of 90 degrees. Similarly, we have in the second moment of area, that's polar moment of that moment of inertia. We say that if there is some axis, where your product of inertia is 0, that's product of inertia is 0. That's equals to integral xy dA. If that equals to 0, then we say that axis equals to principal axis. And usually that we have that axis of symmetry is same as that of principal axis. Let's call it as principal axis 1. So we know that if you have one principal axis, there would be one more principal axis perpendicular that one more would be perpendicular to that principal axis. So second principal axis would be this one. So perpendicular to that, we can write principal axis 2. So this is also symmetric. This is also line of axis of symmetry also. This is also axis of symmetry here. So we say, so second definition of symmetric bending is that if the load passes axis of symmetry or principal axis. Main definition is that principal axis. Then when we have some section, we can say there is some axis of symmetry also that's coinciding with principal axis. But the main thing is that the load passes principal axis. Then we have that we say that the bending would be symmetrical bending. Symmetrical bending. Similarly, if you have a T section, let's talk about T section. So in this one we say there would be one axis of symmetry. So this is one axis of symmetry. So the axis of symmetry is the one where this is also called as principal axis. Where integral xy dA equals to 0. That's principal axis 1. So this is our axis principal axis 1. So one more principal axis would be there. That's making an angle of 90. So there will be one more principal axis 2. So if the load passes along the axis of symmetry, so we say that it is a symmetric bending. Similarly, if your load passes this point, we say that we have a principal axis that's called as symmetric bending. Yeah. And now if you talk about a circle, if you talk about a circle, so we can have infinite number of principal axes. We can have infinite number of principal axes. But they should pass through the centroid now. Let's say this is one principal axis, this is one, and this one. So you have infinite number of principal axes passing through the origin. So you have infinite number of principal axes. It's a similar case that of hydrostatic loading. When you have hydrostatic loading, what we have there, we said you have a Mohr circle of point such that you have stress of sigma on every plane. So we have all principal planes. Infinite principal planes with stress value of sigma. So similarly, we have all principal axes here in case of circle. So we have integral Ixy equals to 0 for that moment that product of inertia is 0. That's integral xy dA is 0, and we have Ixx equals to Iyy, that equals to pi d power 4 by 64. So if you have one more thing that let's talk about now unsymmetric bending. Let's have unsymmetric bending. So you have this section, that angle section. So let's say this is continuous. Now what is happening that let's say this is the section also. This is z direction. This is z direction. This is x direction. This is x direction, and this is y direction. So you are applying moment in z direction. So this is moment m. So you are applying moment in z direction, and because of that you have a I section, and neutral axis is the axis where the bending stress is 0. So that axis forms somewhat in this fashion from this passing through the centroid. So that's we have neutral axis here. It's developed. It's an imaginary line that has developed because of the bending moment. Neutral axis develops in this fashion. So now if you have those two conclusions, that if you draw perpendicular to moment z direction, so we can draw perpendicular to moment z direction. This is perpendicular to moment z direction, that we call as plane of couple or plane of loading. And next one, you draw perpendicular to neutral axis. So you have neutral axis, and perpendicular to this we call it as plane of bending. That means bending would happen in this plane. About this plane bending would happen. So this is plane of bending. So we can say plane of couple does not coincide with plane of bending. So we can say this is unsymmetric bending. Unsymmetric bending. Similarly, if you have that same section, now we say that there is one principal axis that passes in this fashion. This is principal axis 1, and one more would be at perpendicular to this, passing through the centroid. So this is principal axis 2. Now if you say I am applying a load at the centroid, even I am applying load on the centroid, still you can call it as unsymmetric bending. But if you apply load such that it passes in along the principal axis. So this was your load P, and it passes along the principal axis. So we can call this one as symmetric bending. So this one is your symmetric bending. Next one of that we can have that I section also. We can take I section also. I section. Now this is the section. You can have continuous also here. You can make it continuous. Now let's say now you are applying the moment. in the z direction. This is z direction. So you are applying moment in the z direction. So that we can say perpendicular to this direction, z direction, you can have plane of couple. You can have plane of couple, and let's say the neutral axis forms at the centroid. So this is neutral axis. This is neutral axis. So this is neutral axis. So if this is neutral axis, and if you draw perpendicular to that, let's say this is perpendicular. So this we call as plane of bending. So plane of couple equals to plane of bending. So this is symmetric bending, symmetric. Now, if you keep the I section inclined, say if you keep the I section in this fashion, inclined. Let's say you keep the section inclined. Now you are applying moment in z direction. So this is your z direction. This is z direction, and you are applying a moment mz. So perpendicular to that, you have plane of bending, plane of couple, or plane of loading, and the neutral axis forms in this fashion. So neutral axis forms in this fashion. So let's say this is the neutral axis that's forming. This is the neutral axis that forms. This is the neutral axis that forms. So perpendicular to that, you can have perpendicular to that. This is plane of couple, plane of bending. So plane of couple not perpendicular, not similar, coinciding with plane of bending, or not parallel to plane of bending. We say this is unsymmetric bending. Now let's talk about pure bending. This is pure bending. We have studied in the shear force diagram and bending moment diagram that you had a beam, you applied a bending moment M, and you draw a bending moment diagram that was positive BMD, positive M, constant. So bending moment is uniform or constant throughout the length. So that we can say this is pure bending. If you draw shear force diagram, you say this is shear force diagram, 0. And similarly, if you have this one, if you have the supports too, and you are applying load P and P here, so the shear force diagram looks like this way. So this is shear force diagram. So in the mid part we have that shear force 0. Shear force diagram equals to 0. And in that part, if you have bending moment diagram, if you see the bending moment diagram, it looks like this one. So you have a constant bending moment in this part. So the bending moment, let's say this is L/3, this is L/3, and this is L/3. So your shear force are P and minus P. And if you have that bending moment value here, you can say that is equals to PL/3, PL/3. So a constant moment of PL/3 in this part, you can say why the shear force is 0, M is constant. That means that we call as pure bending case, pure bending. Now next one is that, so now if the beam bends, so the beam bends, that we call as pure bending. Now the beam has bent because of the bending moment, and that bending moment was itself only bending moment. There was no shear force along with that. So we said that the bending would be the development of bending would be, we call it as pure bending. Now if we talk about non-uniform bending, non-uniform bending, so that means there would be some shear force also. Let's say you have cantilever and your load P, and the shear force diagram looks like a positive P SFD, and the BMD looks like a linear variation. So M is not linear. It's not linear. It's not, because it is not uniform. It's uniformly varying, but it's not uniform. It's not constant. It's not constant. So we say that the bending that has developed, so there would be bending, some sort of bending would be there. So we say that the bending, it's not pure bending. We say that it's non-uniform bending. So the bending developed, it's non-uniform bending. So let's have the certain examples. Let's talk about that. Certain examples. Say this was your beam, you applied a moment M. Let's say the section that the section of the beam, they say the section of the beam looks like a rectangle. So we have two axes of symmetry. So this is our plane of couple, and this is similar to plane of bending. So similarly, if you have cross section in this fashion, so this is plane of couple, and if you have one more thing that's called as that you can take T section, I section. Let's say this is I section, and this is plane of couple, and all other things triangle. So these are all cases of pure bending, because only bending moment we have applied, pure bending. Now, one thing is that if you have point load, now if you apply point load, and the section is same, and load is along the center, along the principal axis, load is acting, and so we say that is called as non-uniform bending. But the thing is that if you are applying load, let's say you are applying load, but in the cross section, if you analyze in the cross section, this was your principal axis, load passes at some eccentricity. So load is acting on some eccentricity from the centroid or from the principal axis. So similarly, if you have that section of channel section, and it passes, say the load passes through the centroid. If the load passes through the centroid, we still say that it's a asymmetric or unsymmetric bending. Asymmetric bending. That means bending. There is bending also, and there is one more thing that we call as twisting. So twisting occurs because of that torsion. So you are applying moment of P, that is a shear force, and you have developed a twisting moment, that you have developed a twisting curvature. So that's possible only that if you have these features of the section, that load is passing through the centroid in this channel section, and it's even if it's passing through the centroid, so it's passing through the central axis, but it will bend and twist also. Similarly, if you are applying moment in one direction, that we can say it would have an asymmetric bending. That means twisting plus bending. Similarly, you can take L section. Say the centroid here. So load actors here. You have asymmetric bending, or bending plus twisting. Bending plus twisting. Now the thing is that if the load was such that right, for these three statements, for these three examples, you can say if the load was not P, it was not P. If it was only pure bending, if it was pure bending moment, then we say that there is only twisting, there is only bending, there is no twisting. There is only bending, no twisting. So this is one important thing you have to just keep in mind, that if the load was only bending, pure bending moment, that only M is applied. So if you are only M is applied, that means there won't be any that twisting. Twisting would be there, only bending would be there. So let's talk about now assumptions in flexural formulae. So we want to derive that formula, that bending stress formula. For that, you have to say what are the assumptions that we have. Assumptions in flexural formulae. Assumptions. So let's say this is a beam, a cantilever beam. This is the cross section. So you applied a moment mz. Then what will happen that after bending has happened, so let's say after the bending has happened, it would go in this fashion downwards. So initially the section was, initially the section was in this fashion, vertical. So if we say initially the section was vertical, let's say these were the initial sections. This was initial vertical. This was initial vertical. This was initial vertical. It does not look like vertical. Let's say that. Let's say this is vertical. So from the vertical reference, if you say one thing, that plane section, this was the plane section. If you take any section, this was plane section, but it was before bending. That before bending moment was applied, this was plane section before bending. Now if you talk about after bending, after it has bent, what should the section look like? So we say, if the beam has bent, we say the plane format would be, let's say this is the plane. Let's say the plane format in this fashion. We can draw straight lines all. We can draw straight lines. So the assumption one is that if you have plane section before bending, we say that the plane section would remain plane. That would remain plane after bending also. That would remain plane after bending also. So this is assumption one, that plane section before bending remains plane after bending. That if you had plane, that means the section won't deform anything, that won't distort in the shape. That angle between the two axes we can have 90°. Initially the angle was between the two axes 90°, and after that we have also 90°. That means the profile is a linear profile here. There is no change in that shape. There's no change in the shape of that plane, that section. So section remains as a plane. It has not deformed in its shape or geometry. So we say the plane section has remained planed. But if you talk about that, you're not applying pure bending. Let's say you are applying a shear force. Let's say you're applying a concentrated load. Say you're applying a concentrated load at the center. Say this is the center P, and you are applying a load P. So this is the initial thing. So you are applying you're applying a concentrated load. If you say what's the shear force diagram, that's a positive P SFD, and the bending moment diagram is a linear variation, that PL minus PL. So if you now see what's the variation of that because of the bending, how the section has been deformed. So let's say beam bends in this fashion. Now if you draw that, this is the plane, in final plane. Here the shear force is 0. At the end, their shear force, at the end, no, shear force is not 0. So let's make the plane. Let's make the first plane, that this is the first plane, and if you take that reference vertical, if you take vertical reference, let's say this is the vertical reference. This is the vertical reference. This is the vertical reference. Let's say these are the vertical references that we have initially in the plane. So this was our initial plane, that this was our reference plane. This was our reference plane. Now what would happen, that because there is shear force also, we know that because of shear force there is shear stress, and because of shear stress we have shear strain. We have shear strain, and because of shear strain we say that shear strain is the distortion of the shape, or change in geometry, or we can say axis angle change. axis angle change. Angle between the axis changes. The angle between the axis changes. So that means if you have two axes, the angle between the two axes changes in a fashion that, let's say, angle looks like in this one, in this way, that the section performs a miraculous journey in this form, in this way. So your section becomes this one. So you're actually the section, if you draw the section, you can have in this fashion, that section looks like now this one. So this is our section now. So if you say now plane section, this was plane section before bending. Plane section was before bending in this one, in this fashion. This was your plane section before bending. Now the section has become plane section does not remain not plane after bending, not plane after bending. So because of the shear force, there is that distortion of the shape or the section. So this is that when you have assumption, that means the formula is valid only for pure bending moment. But when we derive this equation, we'll be using that for the shear force also. That because the shear force effect is negligible, we say that effect of the shear force for the beams is negligible, for beam slabs is negligible. If the depth is very less, the effect is negligible. So we can write here, if the depth of the section is less, if the depth is less, say of that slab 100 mm, 150 mm, so we say that effect of that warping, we can call it as warping, is negligible. And one more thing is that since you have shear force diagram constant, that means every section is having a shear force value of that P. So shear force is constant on every section. That means the warping effect would be same on that every section. So that warping, the amount of warping would be same. Let's say this is delta, and this is also delta, and this is also delta, and this is also delta. So let's say this was your section. We say this is the, we draw some reference lines. This is our reference planes. Then from that, we say it has deformed in this one, in this fashion. And this is our axis, neutral axis. This is our neutral axis. Not neutral, this is our neutral surface. Let's say this is our neutral surface. And along the section, we can have neutral axis. So this is neutral axis. So let's say it has deformed in this way. So the deformation is same, that amount of warping is same on each of the section. Amount of warping is same. Amount of warping is same on all sections. All sections पे आपका warping effect is same. So we say that because of the shear force diagram is constant, that your amount of warping is also constant. Now if you have uniformly varying load, uniformly distributed load, let's talk about uniformly distributed load. So it's passing through the centroid, centroid of that we can say passing through the principal axis. So if you draw the section, let's say if you draw the section, so let's say load is acting, actually the uniformly distributed load means it's acting for the entire section. Then for the reference, we say it's acting on that center line. Let's make it for the entire section. So this is our cantilever beam. Let's say we draw parallel to this one. So this was our initial beam. This was our initial beam. Let's make it a clear picture. Let's make a clear picture of this one. So let's say this is the cantilever beam. Fix it on this side. So this is cantilever beam. Now you are applying a UDL. So this is our UDL. So this is your UDL. Now what would happen? Say if you draw the shear force diagram, your shear force diagram looks like a linear variation W into L and positive, and a bending moment diagram of that WL square by 2 negative. So your shear force diagram is linear variation. That means maximum shear force is at the support side and 0 on the free side. So if you have that bending, after the bending, so initially the plane section was before the bending, the plane section was looks like this one. So this was our plane section before bending. This was plane section before bending. Now after bending has happened, so the bending profile is like in this way. Let's say this is the profile after the bending. We say that the shear force is 0 here. That means this one would be out without that deformation. So this first one would be without change in the angle between the axes. So this is our first plane that has remained plane. So this one is a plane section. Then, but after that, if you have some reference lines, let's say these are our reference lines. These are our reference lines. Then we have some deformation here. Let's say this is our delta 1. Let's talk about that. This is neutral surface or neutral axis. Then with respect to that, you can have let's say that the deformation here is some amount of delta. Let's say this is delta 1, and similarly you have delta 2. Then after that you have delta 3, then you have delta 4, and finally you have delta 5. So we say deformation at the fifth section is more than delta 4, delta 3, delta 2, delta 1. Because shear force 5 is greater than shear force 4, greater than shear force 3. So your warping goes on increasing as you move towards the side, towards the support. So warping increases as you move towards the side, towards the support, or we can say towards the support where shear force is 0. Shear force increase. So this was the first assumption, that plane section remains plane. Before bending it was plane, and after the bending it would remain plane. So because of that, when we said this would remain plane, because of that you said the section would remain plane. If you analyze that, this was initial, and if you say that plane section would remain plane, that means it would have gone some change because of that deflection, or because of the bending. It has bent in this fashion, but it has remained plane. So initially the plane profile looks like in this one. So plane profile looks in this fashion. So this was our plane profile initially, but after the bending has happened, so it has deformed, or it has bent such that the plane section now remains in this fashion. So this is our plane section now. This is our plane section. Now if we say one more thing is that because of bending, because of bending moment, we know that because of bending moment, say bending moment is positive, sagging, so your top members got compressed. So there is a development of strain on the top side, and you have that stretching of the fibers on the bottom. So you have tensile strain. This was compressive strain, this was tensile strain. Because of the tensile strain, you have tensile stresses, and you have compressive stresses. So we say that, let's say the initial reference was in this one, but the top fibers have elongated by amount of, say, strain 1, strain in compression, and similarly bottom fibers have stretched by amount of some amount of delta t, that then we say that there is some strain. Let's say this is a strain in the tension. Then we say there is a locus of the points where the bending, where the strain is 0, and based on the Hooke's law, we say stress is zero, bending stress is zero. Then we say that there is bending stress zero. That means strain is zero. So if you join them by a straight line, why we are joining them by a straight line? So that's a part of the derivation. We would say that's the part of the derivation. So the main conclusion of the pure plane bending is that plane bending that plane section remains plane. Before bending it was plane, and after bending it would remain plane. That indicates that means that profile linear strain profile. That means linear strain profile. Linear strain profile. So if you have linear strain profile, that indicates your stress profile is also linear. Stress profile is also linear because of the Hooke's law, that stress proportional to strain. So if we want to derive that, we will be deriving this statement. We'll be deriving this statement based on the fact that we have plane section, and we said that it would remain plane after bending. So this was our first that assumption. Let's talk about other assumptions also. Next one is that we say material is homogeneous, isotropic, and obeys Hooke's law, obeys Hooke's law. So this is a must condition. This is the like every concept of the strength of material says that there should be material homogeneous, isotropic, and Hooke's law is valid. So this is that general timeline headline of every theory. And third one is that because we have bending stresses we have tensile stresses and compressive stress. We can say bending tensile stresses and bending compressive stresses. So we say modulus of elasticity in compression equals to modulus of elasticity in tension. This is assumption 1. Assumption 3. Fourth is that beam is prismatic. Firstly, we say beam is prismatic. That means area cross section is constant throughout the length. Throughout the length is constant throughout the length. We don't want to have this one as a variable. For the derivation, we don't want that area also to be variable. On the further studies, we say we can vary the cross section also. But for now, we say that let's keep it as a fixed parameter to just study the influence of that strain and that stress. We want to say what's the effect of the strain and stress only because of that if there was only bending moment that was constant. 5. Next one is that your plane of loading, that we also called as plane of loading or plane of couple is parallel to one of the principal axes, and one thing is that neutral axis, and load passes through load is perpendicular to long axis. Perpendicular to long axis. That means if you have this section, so you're applying moment, the plane of moment on which moment acts, that is this plane. So this plane, we can say this plane is perpendicular to long axis. So similarly, if you're applying load P, that's perpendicular to the long axis. And similarly, plane of that couple, this is our plane of couple also. This is also, because of the symmetry, we say this is plane of couple also. This is perpendicular to principal axis, one of the principal axis. So one of the principal axis is along the long axis, because say from the section, you have this z direction. So you're applying moment mz. So perpendicular to that is the plane of couple. So plane of couple is perpendicular to one of the principal axis. That's principal axis 2. So this is perpendicular to principal axis 2. So we say that let's have the flexural formulae. Let's talk about flexural formulae. Or bending stress formulae. Flexural formulae. That we have also called as bending stress formula. Say you applied bending moment. On the cross section. Yeah, on the beam. Let's say this is the beam of length L. You applied a bending moment. Now, if you say initially the length was L throughout the fibers, every fiber is having length of L. Even at the top and the bottom, everyone is having length of L. Now you have applied a bending moment. Now the thing is that bending would happen. So let's say bending would happen, bending. So top fibers got compressed and bottom fibers elongate. So this is the curvature that's developed. That has developed. So we say there would be some, let's say here the length is L minus delta 1, and here the length is L plus delta 2. Then we say there is some that locus of the points. There is a locus of points where the strain is 0. That means there is no change in length along the points on the length, along the length or along the surface, along the plane. So there is some points along the length where the bending stress is 0, that or strain is 0. So that point, that means the length has remained length L. There's no change in the length L. So it has remained as a length L. Now, if you take this one as reference, so this we call as neutral axis also, or neutral surface also. If you take neutral axis as a reference, because it's not changing the length with respect to original, it's remained original. With respect to the original, it has remained original. So we can take it as a reference for calculation. So if you have this one, we say that the curvature formed is in the form of arc of a circle. We say that it forms the arc of a circle. So if you draw a circle by connecting these points, we say that the circle has formed. So we say that a circle of circle has formed. Let's say that the radius here. So this is the center. Let's say this is the center, and the radius equals to, this is our radius. This is our radius. This is radius r, and it makes an angle of theta. The beam makes an angle of theta. So this is some theta. Let's say this is some theta. So we can say that L equals to r theta. We can say L equals to r theta. That means this length is equals to r theta. L equals to r theta. And if you take that element, if you take a differential element that, let's say this is some element dx. So from the beam, let's say the dx. So these are the two that points A, B, C, D. Let's call them A, B, C, D. So there is some point A, B, C, D. So these are our A, B, C, D, A, B, C, D. So let's say this is A, B, C, D. A, B, C, D. Then we say that let's study this ABCD now. Let's study this ABCD. It's making an angle of, we say that it's making an angle of d theta. So this one is your d theta. And we say that the length of that ABCD, that we have dx element. So the length here is dx. So along the neutral axis, we say that this one would be this one would be dx. This one would be dx. Can you say that what is the value of dx? What is the value of dx? Can you say that value of dx is this one is also radius r. So we say that dx equals to r d theta. Dx equals to r d theta. Then after that, now if you want to say I want to go from the neutral axis, I want to go to a point at a distance y from that neutral axis. So you write that we go to a point y from neutral axis, at a point y away from neutral axis. Point y away from neutral axis. You want to say what's the effect, what's the change in length, or what's the strain developed here. Let's talk about this line now. Let's say can you tell me the length of this arc? What's the length of this arc? One thing is that we can say the radius we can have. This one is also in the form of arc. So we can say this one is your r plus y. This one is your r plus y. So your length of, so this length is equals to say that this length equals to L dash, such that L dash equals to r plus y d theta. R plus y. Yeah, r plus y theta. But if you talk about that on this differential element, if you talk about on this differential element, so we can show that differential element now. So this was your differential element. This was your differential element. This was point A, B, C, D. Then we have neutral axis. So the length here was dx. So dx equals to r d theta, and we go to point y from neutral axis, such that we can say here the length is dx2, that equals to r plus y into d theta. R plus y into d theta. From the circle we have some point here, somewhere circle that center. So we say that length is dx2. So we say that what's the strain at y? What is the strain at y? Strain at y fiber. So strain at y. We say that strain equals to change in length by original length. So final length minus initial length by initial length. So the final length was equals to dx2. Initially the length should have been dx, because when you go from neutral axis to a point y, such that the length was of the differential element length was dx. So every element was having a length of dx. So you go to from dx to minus dx by initially was dx. So when you substitute the values of these parameters, so we can write, so your dx2 was equals to r plus y d theta minus initially was dx equals to r d theta divided by r d theta. So you can get y d theta by r d theta. So your strain at y equals to y d theta by r d theta. So you can say strain equals to y by r. So we can say the radius here, this is the r. R is the radius of curvature. That r is the radius of curvature. Because of bending moment, beam has bent. So because of the bending moment, beam has bent. Beam has bent in the form of arc of a circle. You can say arc of a circle. So when we take the reference neutral axis as the reference line, and we say from this neutral axis you go to a point, you go to the center, the radius formed such that the neutral axis makes some circle. So the circle formed along the neutral axis, that makes some center, and there is some radius r. That radius r, that we have radius of curvature, and in the design we say 1 by r, that's curvature of beam, that we call as curvature of beam. In design we use 1 by r also. We have studied in the deflection that d2y by dx2, that equals to 1 by r. So we got this one also. Now the conclusion is that, based on the fact that we said plane section remains plane after plane section before bending remains plane after bending. So that conclusion gave you a result that strain is proportional to stress. That strain is proportional to the distance from the neutral axis. That y is from the neutral axis. Important one. Y is the distance from neutral axis. Distance of, you can write distance of any fiber from neutral axis. So the conclusion is that, say you have fiber, you have this section, this is the z direction, and this is y direction. So if you go from neutral axis, so to a point y, or any point y downwards, so you have a strain here. That is that's a function of y. That's a function of y also. That means the strain is 0 at the neutral axis. So if you have strain at the neutral axis, that's 0. So strain is 0 at the neutral axis. Then there's a linear variation with that of y. So we have strain proportional to y. Similarly, you have a strain that's proportional to y. Strain proportional to y. Then from the reference plane, if you have reference plane, you say that the strain is developed are linearly proportional to the distance from the neutral axis. So this is we can write strain variation profile, strain variation along the section. This is the section. So this is for the entire that if you have entire length, then you can have that. So you can say that entire length is having this this profile, entire length. So this is that strain proportional to strain. But one thing is that we said that Hooke's law is valid. We said that Hooke's law is valid. Now from that, if the Hooke's law is valid, we have stress proportional to strain, and we have stress equals to E into epsilon. That means sigma equals to E y by r. That means the stress, bending stress at any fiber is a function of y. It is a linear function of y. So if you draw the stress profile also, you say this is the reference profile. There is some point on the section where the bending stress is 0. So we say then bending stress is a linear function of that distance from the neutral axis. So your bending stress, this is your stress profile, you can say bending stress profile. And we said that because of sagging bending moment, because of the bending moment was positive, sagging bending moment. So we said top fibers have compressed. So on the top fibers, you can show that it's compression. And there is some sigma compressive stress on the top maximum, and similarly there is some tensile stress maximum at the bottom. You can say it's sigma tensile bending and sigma compression bending. And this is, we can show that this one, we can show that tensile stress can show away from the fiber. So we can show it in this way. Similarly, you have strains. Here the strains are that compressive, and here the strains are tensile. So you can say these are your compressive strain, and this is your tensile strains. So this diagram represents that. Say this diagram, because of this effect, this is net compressive stress sigma, say that compressive stress, and because of this effect, you can say this is some force here, F, you can say T, because of the symmetry, because of that force equilibrium, you can say force equilibrium C equals to F, because there is no external force on the section. So because there was only bending moment applied, there was no shear force or any other external force. And you take any section, if you see what's happening in the section, you say there is some compressive stress is developed, and there is some that tensile stress is developed, and there is some neutral axis. So this is compressive and this is tensile, net tensile. So they are balancing each other based on the conservation of that force equilibrium if Fx goes to 0. So if we talk about now, that it's the same thing. Say you had a beam. Now you applied bending moment. So you applied a bending moment M. Now there should be some internal bending capacity, or we can say there should be some resistance to moment that we call as moment of resistance. There's some resisting moment or moment of resistance. Let's call that as MR. That's moment of resistance. So if you take any section, let's take any section. So there should be some internal moment. There should be some internal moment that we can call as moment of resistance. So if you take that section now, this red section. So if you say so the moment is contributed by this section. So to balance this one, so you're applying M, and there should be some internal moment here. So this moment is that developed by the section. It's developed by the section. How can the section develop some moment? So let's say we have shown you how it has developed. The thing is that actually this is the reason how the bending stress is getting developed. That resistance, moment of resistance is getting developed, compressive and tensile. So to make that now in in a mathematical way, you can say, let's say that this is the reference line, that neutral axis line, and this is the section cut. This is the section cut. I want to say from if you go from a y, if you go y distance from neutral axis, and if you take any differential area element, you take a differential element of area element. If you take differential area dA, then you say how much moment it contributes, because that moment was mr, it's contributed by the section. It is contributed by section of area cross section equals to a. That a is the integral of small dA, isn't it? That a dA is this integral of that a is the contribution of small dA. Let's say this dA, let's say this contributes small moment of resistance dmr, and that equals to, so it resists some force. We can say that resists some force f. Let's call it as fy or fx. Let's call it as, that means let's call it as fx. That means at a distance x from one of the supports, it has resisted a force of fx, and we have some lever arm also, that we can say this is the that perpendicular distance. So this is your y, because your bending stress is along the x-axis. Bending stress, we can say this is the bending stress. This is along the x-axis. So we say that fx into y. So if we say what's the total moment of resistance that has developed because of that entire section, we can write that equals to integral, yeah, this was initially fx into y, so it would be fx integral fxy. But if you know what's the value of stress, that we know that stress equals to force by area. Similarly, if you write fx, that equals to the stress that has developed at that section from distance x from any support. So sigma x into area of that cross section, but it has a small, so it is contributing small force df. So it's contributing small force dfx. So similarly, it's having a small area of areas, that dA. Then you have sigma x dA into y. So finally, you got this one. So to revise this thing, we can say you are applying a bending moment of m. Now to balance this moment at any section, you said there should be some internal moment that has developed, that we call as a moment of resistance. So that moment of resistance is contributed by that section. So that section has some area of total A. So if you have that section of area A, and you go from neutral axis to a point at a distance of y, you take a differential element of area dA, you say that how much moment it's contributing out of that total moment of resistance, how much moment it's contributing. You said it will contribute small dmr, that equals to small force into that lever arm y. Then we have to say that what's that value of small force. That small force, we know small force equals to small stress into small area. So but the stress, we know that stress is uniform. Stress remains constant on a section. Stress is constant on a section. No. So we say that sigma x into dA, small area, it contributes to small stress. Then finally that force dF equals to sigma x dA and into y. So, but based on the equation we have earlier, that we had that sigma equals to Ey by R. Sigma equals to Ey by R. That bending stress equals to Ey by R. If you substitute here that Ey by R, and you have already dA into y integral, that means E by R integral y square dA. That's your moment of resistance mr. Now, what you would say, what's this value? Integral y dA, y square dA. That is the second moment of area. Second moment of area. That's y into dA. So second moment of area. That we say that equals to E by R. That's moment of inertia, but it's about the neutral axis because y is from the neutral axis. So we say moment of resistance, that equals to E by R into I neutral axis. So your moment of resistance, we know that moment of resistance equals to moment of resistance We know that moment of resistance. We have that moment of resistance should be equals to moment external moment. So you had applied a moment. You have applied a moment that was in the z direction. So you can call it as mz. So your moment resistance was equals to mz, and neutral axis, and there's a neutral axis which is along the zz section. So this was your zz axis, and this is also neutral axis. So you can substitute, you can simplify or modify it in this way, that moment z equals to E by R and IZZ. So your moment, the bending moment developed, you can say the bending moment developed at any section. The moment you applied at any section, it's equals to E by R IZZ. So if you want to say I have applied a bending moment, if I have applied a bending moment of M equals to 100 kilonewton meter. So applied a 100 kilonewton meter external bending moment. Your member is having a value of E that's also constant, and a radius R. So your variable is that your IZZ. So you want to say which section I should prefer, such that your IZZ will balance that moment Z. So now we got two equations. So if we say initially we got that sigma equals to EY by R, and now we got mz equals to E by R into IZZ. So we have E by R and E by R. If you make a general equation that says that sigma by Y equals to M by I equals to E by R. So this is your general equation, that mz by IZZ, you can keep it as it is. So similarly, if you are dealing with the moment in Y, so this was your ZZ axis. Now if you are applying moment in Y direction, so this is Y direction, so you are applying moment in MY. Similarly this one, so you are applying moment in MY. So it would deform the beam in this way. So beam would be deflected in this way. So this way. So we can write also sigma by Y. The bending stress is in X direction. You can write sigma X. So sigma X. The Y is from the neutral axis. So if Y is from the neutral axis, so you have section. So this was your ZZ section, ZZ axis, and this was YY axis. And neutral axis was parallel to ZZ axis. So Y you take from Y. So Y, the value of Y is from that from the neutral axis that was parallel to ZZ axis. And if you take for this case, if you take that sigma X equals to sigma X by Y equals to MY by IYY equals to E by R. So now the value of Y should not be here that same Y. It should be now if you say the neutral axis would be for the second case, moment is in the Y direction. So moment is in the Y direction. So this is our section. So moment is in this direction. So this is your YY direction. Moment is in this direction. So we have perpendicular to this plane of couple, and perpendicular to that neutral axis. Neutral axis is also in the same direction, and perpendicular to that we have plane of bending. That means plane of bending is in this fashion. So in this fashion, this is plane of bending. So with respect to that, your beam is bending in this way. So plane of bending is that. So we say that your from the neutral axis, if you take any section, you have to go at a distance z. So this is our neutral. From the neutral axis, you have to go at a distance z, not from y. So initially you are going from neutral axis was this one, so you are going from neutral axis up to a distance y, because this was your y along the yy. Now you have to go along the zz. Along the zz, you have to take that element. So you have to go z at a distance z. So you can write sigma x by z equals my by iyy, and the moment of inertia is here. We can say this would be equals to integral. This would be equal. If you derive the equation, same equation for along the z, y moment my, you can get integral z square dA, that equals to iyy. So this is the general equation of that flexural formulae. So your bending stress is related to bending moment, and and y is the distance of that fiber. That means that means the bending stress, if you write the bending stress, is my by I. That means how much bending stress is at a location y, that's from the neutral axis. From the neutral axis, how much bending stress has developed on a beam, fiber, on cross section. That's a point on that section, that's at a distance y from that neutral axis. How much bending stress is that there? And that means the bending stress is also directly proportional to y. So if you say my value, the value of y is 0, that means your bending stress is 0. So a linear variation of bending stress. Now one more thing is that if you talk about you have, because you are applying only bending moment along the length. So this was your beam. So you applied bending moments. So if you say summation of external forces, summation of horizontal forces equals to 0, because there is no horizontal force at any section. There is no horizontal force at any section. You say summation of forces should be equals to 0. But if you say what is the value of force, the value of force was equals to sigma x dA on the section, that equals to 0. But if you use what is the value of sigma? Sigma was equals to Ey by R dA. So if you integrate it, that's equals to 0. That means that once you integrate it, you would get a value of E by R into A into Y bar equals to 0. So your Y bar equals to 0. That means your Y bar equals to 0. This indicates that. So we can name this Y bar as that centroidal distance. Or we can say distance of centroidal axis. Is 0 from neutral axis. That concludes that if you have a section and there is some centroidal axis, let's say this is the centroid and this is the centroidal axis. If you go to a distance of y equals to 0 from neutral axis, and you would receive centroidal axis. That means neutral axis coincides centroidal axis. So neutral axis coincides centroidal axis. That means if you say this is my centroid, that means it's also the neutral axis. One more concept is that we call as section modulus. So this is the z that we write as z, that equals to I neutral axis. So section modulus about centroidal axis, we call it as section modulus about centroidal axis. That equals to I neutral axis by y max. What is this y max? So you have this neutral axis, you have y, and you have y. So we know that neutral axis for this beam, that's a rectangular beam, would be at the mid. That's at the mid. If the member is equally strong in compression and tension, that means the neutral axis would be at the mid. If you write here for equally strong in tension and compression, equally strong in tension and compression, in compression and tension, you can have neutral axis at the mid. That means y equals to some depth by 2 and depth by 2. So total depth is d. So your y max equals to d by 2. So y max equals to d by 2. You can write I neutral axis by y max is d by 2. Now if you have section size that dimensions change in this way. So we say that the centroidal axis is the neutral axis. So your centroidal axis will be, this is your centroidal axis, and that's also neutral axis. So this is your y1, and this one is your y2. So we write what's the value of z about the centroidal axis, section modulus about centroidal axis, that is I by y max. But I is about neutral axis, and y max, which of these is y max? We can say y max looks like that, y2 should be y max. So this is the, we can say, distance of the extreme fiber from the neutral axis, that is y2. So that you can write I neutral axis by y2. I neutral axis by y2. So this was the end of that first topic of bending stresses. So if we want to take more things, let's talk about more things. Let's say we have more moment of resistance. Now let's talk about moment of resistance. Moment of resistance. Moment of resistance. So we say that it's the maximum bending moment. It's the maximum bending moment that can be resisted by the section, without going failure, without undergoing failure. So we say that the failure should not be there, and how much maximum bending moment it can resist, the section can resist. We say that that is equals to moment of resistance, and from the bending stress formula we say m equals to sigma m by r, m by I equals to sigma by y. That means moment of resistance, we can say that equals to sigma y by I. So we know that I by y, if you talk about y max, we can say that equals to sigma how much permissible stress you can allow in the material, permissible stress into your section modulus of that section. Your z is the function of section. So which section you have, accordingly your section modulus changes, and how much material. So for the material section, that stress is constant. Permissible stress is constant for the material. So if the section was different but material was same, say you have steel sections. So this was all steel. That means your permissible stress is same, sigma permissible. That equals to some yield stress divided by some factor of safety. We don't want to go beyond yield stress. We say let's keep the stresses below the yield stress. So your moment of resistance, that equals to sigma permissible, that's sigma yielded by factor of safety into your z section modulus. So if you have a beam, say if you have beam propped cantilever, so you apply the UDL. Let's talk about that. You apply the UDL, and the bending moment diagram looks like in this fashion. So your bending moment is maximum somewhere here. Let's call it as M2. This is M1. Some negative bending moment. This is positive. This is negative. M3. So we say let's call it as this is ABC. So your beam is ABC. So now the two possibilities arise. Two possibilities arise for the design. Two possibilities arise. First one is that if you want to say I want a beam of uniform length, uniform cross section. If you want prismatic beam, if you want prismatic ABC, prismatic AB equals to B, AB beam and BC beam, or we can say directly ABC. Prismatic area cross section is same, entire length. For the entire length, you want to say my cross section should be remain same. Then how can you design this beam? So we can say out of those three bending moments, maximum bending moments, you say how much we say permissible stress we have same, and section modulus, how much section modulus should I keep? Such that that moment of resistance, the moment of resistance should be equals to, this one, that should be equals to maximum of out of these three, M1, M2, M3. So we can say out of those three bending moments, external bending moments you applied M1, M2, M3, which of them have maximum value, then that should be resisted by the section. So for the section to be safe, you should have a section modulus. So you should have some geometrical property of the section such that it can balance that maximum out of these three. Now if you want, for second case, if you say that I want area cross section for AB different for as that of area cross section for BC section. So you want to say I want an area of cross section such that here the area is such they say this is the, here I want area of cross section. So this is area of cross section here, and similarly I want a cross section, small cross section here. I want a small cross section here, small a. So I want a different cross section. So how can I design this one? So based upon this one, you can say now For the BC, you have only one bending moment acting, so you have only M3 acting. So if you want to design, BC section, design for BC section, you would say your M3 should be equals to moment of resistance of BC, and that should be equals to sigma permissible into Z for BC. How much section modulus I should keep for BC? Accordingly, you can design for M3. Similarly, if you want to design for member AB section, you want to say out of these three, you only have two bending moments acting for the BC. So you have two bending moments acting for the BC. So you have this one M1 and M2, M1 and M2. You would say maximum of M1, M2 that you can design for as moment of resistance for AB, that equals to sigma permissible into bending stress, that section modulus of AB. Now the concept of section modulus for the different sections. Let's calculate that. So you have section modulus. So we got that moment of resistance is sigma times Z. So your moment of resistance would be more if your section modulus is more. That means more bending strength. For more bending strength, you should have a section that has more bending, that section modulus Z. Now, if you take a rectangular section, this is a rectangular section. So you have a depth of D and a width of B. Then you have neutral axis NA. You can call it I neutral axis equals to, we know that जिस एक्सिस को काटे उसका क्यूब, यहाँ पे जिस एक्सिस को काटे उसका क्यूब. So your neutral axis is cutting which section? It's cutting which length? It's cutting D. So you have to write BD cube by 12. Now, if you want to say what's the value of Y max, so for this beam of a rectangular section, we say Y max equals to D by 2. Either you go from towards top, or you go from bottom to downwards. If you go downwards, you would have same value of Y max equals to D by 2. So your Z becomes BD cube by 12 and D by 2. So your value of BD squared by 6. Now, if you want to keep it in this way, such that you are having neutral axis in this direction. This was your neutral axis because you have applied moment in Y direction. This was ZZ direction, and this was YY direction. You are applying moment in Y direction. In this case, you are applying moment in Z direction. Now, if you apply moment in Y direction, this neutral axis would become parallel to YY direction. So such that now we would say what's the value of I neutral axis? What's the value of I neutral axis? That we equals to जिसको काटे it cuts the B. So we can write B cube, and your D is that uncut. So we can write DB cube by 12. And your Y max, if you want to say what's the value of Y max, you can't say what's the value of Y max. You should say what's the value of Z max. You can write value of Z max. Z max equals to value of Z max equals to. So this is Z. So maximum value you can go to B by 2. So finally your section modulus along YY. So we can write that equals to DB squared by 6. Similarly, if you have a circular cross section, this is your neutral axis, and the maximum Y can go to D by 2, Y max. On both sides, it can go to Y max of D by 2. So you can write I neutral axis by Y max, that equals to Z. We know that that moment of inertia of circular section about neutral axis, that equals to pi d power 4 by 64. And because neutral axis is centroidal axis, so we can say NA equals to ICA. And similarly, Y max is your D by 2. So we got a value of pi d cube by 32. Similarly, if you want to say you have they have a triangular section, so such that that centroidal axis is here, that is same as that of a neutral axis. We have this depth of D by 3, and this one would be 2D by 3. So Y max would be 2D by 3. So we can write I neutral axis. So Z value equals BD cube by 36 and divided by 2D by 3. So you got a value of BD square by 24. BD square by 24. BD square by 24. Now, if you use a tube section, let's say this is a section, this is a tube section. So only material available is along this periphery, that in the mid you have hollow section. So you can call it as hollow section or tube section, hollow or tube section. So you have external diameter of D outer, you have internal diameter of D internal. So if I want to say what's the about the neutral axis, what's the value of that second moment of area, we can write that as, say, assume that it was a full solid, we can write pi d outer power 4 by 64, but you have to subtract the hollow part because there is no material inside, so you can write pi d inner power 4 by 64. And what's the value of y max? The value of y max, what the solid is, that's d outer by 2. So you can say d outer by 2. So okay, you got a value of pi d power 4 minus d inner power 4 divided by 32 d outer. So this is your z value of z about centroidal axis, so you can keep it as a z value. So this is about the section modulus. This was about the section modulus. Now, if you want to say, I want let's write that moment of inertia calculation or second moment of area calculation. So we have two theorems. One is your parallel axis theorem. Next one is your perpendicular axis theorem. So let's say this, you are having some area. Of the cross section A, and the centroid here is at point. So we can call it as GG or neutral axis. So want to say about a line AB. This is your line AB. You want to say what's the value of second moment of area about the line AB. So let's say this is at a distance of D1 from the centroid. So we can write the IAB equals to the value of inertia, that moment of inertia of that body of that area about its own centroidal axis IG1 plus that area into that D square D1 square. Similarly, if you have this section, now we say that this one is your along the ZZ direction. This is your ZZ direction. So this is your IZZ, and this one is your along the YY direction. So we can call it as IYY. So if you want to say what's the value of that second moment of area about the Z direction that is perpendicular to that is, we can call it as IXX. So we can write that equals to IZZ plus IYY, that by perpendicular axis theorem. Let's have a composite section that you have area 1, then you have area 2, then you have area 3. Centroid is here, centroid is here, centroid is here, and you have lines of some line of AB. You want to say what's the total that moment of inertia about the line AB. So let's say this area A3 is at a distance of D3 from the line. The centroid is at a distance of D3. This one is at a distance of D2, and this one is at a distance of D1. So we can write IG1 plus IG2 plus IG3 plus A1 D1 square plus A2 D2 square plus A3 D3 square. So we write one more statement that we call as justification of use of I section as a beam. So we prefer a beam which is having a shape of I. So we prefer this section in place of beam that's a rectangular section. We prefer I section. Want to say why we prefer this one? So you have We know that moment of resistance is equals to sigma permissible into Z section modulus. So if you want to say if you are limited that depth, if you are limited depth, that means if D is limited, if the depth is limited, say for the same value of y from the neutral axis. So this is neutral axis from the same value, for the same value of y. So for same value of y, we know that z equals to I by y. So that means z is proportional to I. So if you want to have z more, because if you want to say I should have more moment of resistance, I should have more bending strength, that means your z should be more. And for particular value of y, your z is only more when your I is more. If your I is more, that means more area is away from the neutral axis. More area is away from neutral axis. So if your more area is away from the neutral axis, say let's say you have some rectangle which having some area of say this is area A and this is also area A, so total area of 2A, and you want to distribute this area in such a way such that the maximum value of y is same for both the beams. Let's say total area is same, total y is same. Now you have used this area equals to A and same area equals to this one A, but you have distributed the area away from this line, Now if you use parallel axis theorem, you would say what's the value of I about this line that we call as neutral axis, that equals to area about the centroid area about the centroid IGA plus that area into that y square, you can say, and that into 2 because we have 2 area. Similarly, if you use for the first one, they have centroid here, so you have centroid here. The value of centroid would be same, the value of I would be same, some sort of same value, but that by parallel axis theorem, this value would be very less. So we increase this value of AD square in the I section such that your value of I becomes more. So we increase by parallel axis theorem, concept of parallel axis theorem. So we increase this AD square by increasing this depth of this area away from the neutral axis, by increasing the distance of this area from the neutral axis. So we say that the I value increases for the I section. So your more area is away from the neutral axis. That's why. So we can have this conclusion that in this way, that moment of resistance, we want moment of resistance increase. That means bending strength increase. That's only possible if Z is more, bending that section modulus is more. That's only possible for if you fix Y, because you have limited space, limited depth. You have constraint in that depth. So you for particular Y, you can have I more. That means more area should be away from the neutral axis. Now, if you want to calculate that moment of resistance, that we already calculated, that you applied a moment M, then we say there should be some internal moment that we call as MOR. So that MR, moment of resistance, we calculated that earlier by this concept that you go from neutral axis to a point, you take a differential element of area dA at a distance y from neutral axis, and then you do small dmr equals to small df into that y. Then you got that m equals to sigma y by I or sigma e by r, some value of that sigma, that ey by r, some value you got. So finally, if you want to calculate it by next method that we call as internal couple method, its hint I have already provided you. Internal couple method. So you take that section. Let's take that section. We know that on the top fibers would be having compression and bottom fibers having tension. Let's say that you can show this in this way. Let's say top fibers having compressive strains, that means compressive stresses, and bottom fibers having tensile strains and tensile stresses. So this is tensile stresses on this section. So this is neutral axis. So we say there's some resultant value of that sigma c into some area. So we get a compressive stress of C. on this section and some compressive tensile stress of T. So we know that the variation is linear. That means the that shape format is a triangular variation. That's a triangle, and this one is also a triangle. And we know that centroid would be at the resultant would be acting at the centroid. At the centroid. So this distance would be that let's say this distance total depth of the section is, let's say total depth of the section is d. So we can write this is d by 2 and this is d by 2, and finally we can write this one is as equals to 1/3 of d by 2. So your centroid is acting at d by 6 from the ends, from the top fibers and bottom fibers. You have a centroid of those resultants acting at d by 6. So if you write that summation of forces equals to 0, summation of horizontal forces equals to 0, that means C equals to F. That means C equals to F. So what's the value of C? Can you calculate the value of C and F? Or we can write tension. So what's the value of C? So your compressive value, force, we know that stress equals to compressive force by area. Do we know that? So we want to say what's the value of sigma C and what's the value of sigma T. Now one thing is that let's take this case as a, let's write the headline of this this topic. Along with the internal coupled material, you write that we want a beam of equal strength in compression and tension. So if you want to say my bending stress in compression and tension should be same, that means you have a sigma allowable here same as that of sigma allowable here. So that means sigma T equals to sigma C. That means maximum stress you can allow in tension equals to maximum stresses you can allow in compression. So if you write both as equals to sigma, so you can say the value of that sigma equals to force by area. So your C value was equals to, yeah, C value. So that means C value equals to sigma into A. Can you say that sigma into A? So what is the area it's contributing? For the compressive force, how much area it's contributing? We can say half of the section. We can say half of the section is getting compressed. We can say half of the section, this is neutral axis. So half of the section is getting compressive stresses or compressive force. Why? Because compressive strains. From compressive strains, you have compressive stresses. Similarly, half of the part of the section, so it is receiving tensile stresses. If you want to say what's the area of this part, you can say that's equals to some depth into d by 2 into your width of B. And we know that stress is varying from 0 to sigma allowable along this depth. So if we want to say what's the value of sigma, what's the value of C, that we can write that as sigma average into A. We can write now, because that along this depth d by 2, your sigma is varying from 0 to sigma allowable. So we can do average because it's a linear variation. So we can write sigma minus 0 by 2 into area of B into d by 2. So we got a value of sigma into BD by 4. So your it's a compressive force of sigma BD by 4. That's also tensile force equals to tensile force. Now you want to say what's the value of moment of resistance based on the internal couple method. So there should be some couple developed. So there should be some C acting here and there should be some T acting at a distance of Z. So such that the couple is formed MOR, that we call as moment of resistance. So if you want to say what is the value of Z, so the value of Z should be equals to this one. Z should be equals to total depth of D minus you have this force acting at d by 6 from the end fibers. This is d by 6. That means we can write 2 times d by 6. So if you want to say what's the value of moment of resistance, that we can say that's internal couple developed, that equals to C into Z or T into Z. So we can write sigma BD by 4 into D minus 2D by 6. So finally you can receive a value of moment of resistance equals to sigma times BD squared by 6. That equals to sigma. Let's call it as sigma allowable into section modulus of that section. MR into Z, BT square by 6. So we can say moment of resistance equals to sigma allowable into Z. Or we can say this is also equals to sigma into Z. Z value of Z was I by Y. I neutral axis about by Y max. We are left with this one also. Now you want to say now you take example of, let's say, cast iron, or you can take example of concrete. These examples are these materials are, we say, they are weak in tension. They fail earlier in tension because they are brittle. We know that brittle material fails earlier in tensile stresses, sigma 1. They are weak in tension but strong in compression. Sigma 2. We can say compressive stress. This should be compressive stress, sigma 2. It should be compressive, negative sigma. But weak in tension. The tensile stresses, they are weak in. So for that, now we know that for the bending stresses, we have compressive stresses here and bending stress, tensile stresses here. Now, if you want to say, I want a material which is having sigma T not equals to sigma C, such that we say, let's talk about these two, such that sigma C greater than sigma T. That means they can allow more bending stresses in compression than that of tensile stresses. So for that, how can you design this section? How can you design this section? How can you take this depth D1 and depth D2? How can you design the section? Where should be the location of neutral axis? Let's say you design in such a way that your neutral axis is somewhere here, because your centroidal axis is somewhere here. Let's say you design it in such a way that bending stresses, you receive bending stresses of sigma C allowable, and you receive a tensile stress of sigma T allowable, and this is your reference. So let's join them, and you want to say, I want to use the material fully. I want to fully utilize the material fully. If you want to utilize the material fully, that we can say economical utilization of material. We want to say the sigma T allowable should reach at the same time as that of sigma C allowable. That means on both the sides the materials should have reach the stresses of allowable stresses. That means the material, if you want to fail the material, it should fail on both the sides simultaneously. We can write simultaneously. They should reach this value simultaneously. This is the economical design for the material. If it is the material that's not equally strong in compression and tension, it's not equally strong in compression and tension. So for that, you want to say how should I design? We can say, by the linear variation, we say sigma C for depth of D1, that should be equals to sigma T for the depth of D2. So this is the design approach that we allow. That means from the tests you have performed, that you know that for the say cast iron, tensile stresses, how much you can allow. Let's say you can allow A, and sigma, how much compressive stress you can allow. Let's say you can allow B. Now you want to say, I use a section such that its neutral axis at a distance of D1 and D2. How much should be D1 and D2? You say, if you want to use the material fully, or the stresses should reach simultaneously, you said keep the value of D1 by D2 such that it equals to A by B or B by A. So now in the next lecture we'll be taking the problems of those bending stresses. Thank you for watching this lecture on the bending stresses derivation and the beginning concepts.